All right, we should be live now. All right. Hi, everybody. I hope you're having a great JuliaCon 2022. Um, I just wanted to quickly remind you all to, sign up for the conference via Eventbrite and join the conference platform, which is Discord. And hopefully, you all have all of that set up. And if you don't, please ask on the JuliaCon channel on Slack and ping one of the organizers, and we're happy to help. Um, I wanted to quickly thank all our sponsors, our platinum sponsors, especially Julia Computing, Relational AI, and Julius Technologies, from whom we'll hear from very shortly. Our gold sponsors, Intel and AWS, and our silver sponsors, Beacon Biosignals, Pumas AI, QEra Computing, Conning, Invenia, MetaLens, ASML, G Research, and Jeffrey Sanoff. We also want to thank our media partners, Pack Publishing, Gather, and Vercel, and our community partners, Data Umbrella and WIMLDS, Women in ML and Data Science, and our fiscal sponsor, of course, NumFocus. So let me quickly kick things off and hand it off to James Lee from Julius Tech. Julius offers an auto-scaling, low-code graph computing solution that allows organizations to quickly build transparent and adaptable data analytics pipelines. Graph computing is an innovative technology that enables developers to organize pipelines as directed acyclic graphs, which are tags, as many of you all know, and can be applied to many enterprise use cases, including explainable ML, data processing and transformation, AAD, and more. For Julia users, they provide a dynamic set of tools to help developers solve enterprise scale data analytics problems and to integrate with existing tech stacks. I'll hand it off to James Lee, the CEO of Julius Technologies. Take it away, James.
All right, thank you. Welcome to the Julius Technologies presentation. We're really excited to be here as a sponsor and Julia advocate. As Ranjan mentioned, my name is James, and I'm the CEO and co-founder of Julius Technologies. And we're a company founded by experts in the fields of computational finance and graph computing. Our team has built some of the most complex data and analytics systems at global investment firms, and we have decades of practical hands-on experience addressing the challenges that engineers typically face when building enterprise scale pipelines. I can remember back when I was running a trading business, there was a model upgrade that we'd spent almost a year working on that produced wildly erroneous risk numbers. It took us weeks to find out what happened, which in trading terms is a lifetime. Now, it turns out in our original system, there was an algorithm buried deep in the code stack, which would multiply our output by -1, programmed by a developer who was long gone, with no supporting documentation to explain why it was there. But that's the nature of enterprise computing. You may have started with a clean and simple pipeline to solve a particular problem, but as your business grows, so does the complexity. With too many moving parts and technologies and a bloated code base, it becomes almost impossible to explain how and why your system works the way it does. The key problem here is that there's no visibility into what's going on, or more specifically, no data or analytics lineage to simplify troubleshooting and to help developers explain the output that they're actually seeing. When you add to that the constant need to re engineer pipelines to scale to growing business demands, you're inevitably left with a situation where it's extremely difficult and expensive to deliver data insights quickly. Now, we used to call this setup the 80/20 rule because engineers spent 80% of their time on managing lineage and scalability related issues and only 20% on actually building models and solving business problems. At Julius Technologies, we're helping companies reverse that ratio. We offer a low code solution for building and managing data analytics pipelines via graph computing that supports lineage and auto scaling out of the box. So, how's this possible? We combine the best of Julia and its high performance with the transparency and lineage of graph computing and a low code framework that enables easy graph creation and auto scaling. The net result is a truly revolutionary solution for building enterprise scale data analytics pipelines. Let's be clear about what we mean by graph computing. Graph computing is a powerful technology that allows organizations to build complex pipelines as a directed acyclic graph, or DAG. A DAG is a generic representation of any kind of computing, which is fundamentally just a collection of data transformations. Any computation, from the simplest formula to the most complex enterprise systems, can be reduced to a DAG. But the takeaway here is that DAGs are a perfect representation for building generic solutions to lineage and scaling challenges because they natively track all the data and analytical dependencies. But graph computing in itself isn't enough. Traditional graph solutions are difficult to use and adapt. They require a great deal of coding and are often limited in terms of their scalability. At Julius, we created a low code framework that makes it easy for developers to define and create sophisticated graphs, and also automates and optimizes difficult tasks like distribution and resource management. As a result, Julius graphs are simple to build and extremely fast and scalable, ideal for handling real world problems. So let's talk about performance. Here we see the results of a benchmark study showing how Julius is 10 to 1,000 times faster than the leading alternatives. You can see as the graph size increases up to 500,000 nodes, the competing platforms hit their limits, whereas it takes Julius only 15 seconds to run on a single computer. You can test these results for yourself on our developer environment, which is free for developers to sign up and use. So now let's go through a few applications of Julius using real world examples. So the first example we're going to show is an accurate reproduction of a bank's ML pipeline for credit approval. Here on the screen, we're showing the process for a couple applying for a credit line increase. So here you can see the entire machine learning training application from beginning to end, from the raw data to feature engineering, the training of the model, and then using the model for inference and reporting the final results. The graph representation is very intuitive. Here, the different colored nodes represent different physical machines. The workload in this case is automatically distributed to 4 different boxes. So for example, all the yellow nodes are executed by the same physical machine. Now let's look at how this application works. In the beginning, this is the raw data, which can be retrieved from any data source. That could be a relational database, public URL, unstructured. We have connectors from many different data sources, but developers are free to build their own as well. Then we can do a quick visualization of the data. We see a histogram here, but we can also measure for completeness and data quality. And then downstream, we can click on any node and visualize the data as of that point in the process. If we look at this node, we've added a few additional columns to the initial data. For example, one of the columns is called liar, which tracks whether or not certain conditions have been met on the initial application. If these constraints are broken, it means the applicant has lied on their application form. And down the road, we're training a decision tree model, which is a standard model sourced from an existing Python library. So one key point here is that no matter what analytics library you have, we can easily interface and source them from either your proprietary library or third party or open source library. All of that can be easily plugged in. That includes libraries written in C++, Java, R, .NET, and of course, Julia. So in this case, we're using a mature Python library to build the decision tree, and you can even drill down to visualize what the category decision tree looks like. As you can see, it's just a very typical tree that branches out using different attributes, and eventually in the leaf node, you're getting the default probability forecast for all the entries that fall into that bucket. So it's very intuitive to visualize how the logic works. For example, we can easily see that the most important attribute to look at is whether this couple is married, and you can follow the logic forward. Going back to the top level, the reason we have a multi-level display is to allow you to drill down to the smallest details if you want to see how something works internally, but also have the benefit to visualize an uncluttered top level to get an overview of the process and to navigate the graph. Further up the graph, we have the forecast of the default probabilities, and we have the various metrics for accuracy. For example, here we show the ROC curves and accuracy rate with different views. Now here, we also integrated the model documentation process into the same pipeline. So a developer can describe the corresponding data and analytics for any node, and with a single click, we can generate the entire end-to-end documentation with the actual live data populated. Changing the pipeline in this case will change the corresponding documentation automatically. So this is really useful for governance and control by automating most of the manual labor involved. So this is a self-contained application that highlights a few key benefits that Julius offers. The first is that a graph provides for complete transparency and lineage. For any node, you can just click and get the data and analytical logic behind the calculation, which makes the pipeline much easier to support and debug. For example, you can see what calculations go into any particular node. You can see the complete lineage, and you can also show the dependencies. What are the downstream dependencies that are derived from this particular data point? Making scenario analysis much easier because whenever you change any of the inputs, you don't have to recompute the entire graph. You can just compute those dependent nodes. So scenario analysis becomes much faster. So that's one benefit from having complete lineage and visibility, fast scenario analysis, which comes from using a DAG. So the second benefit is the auto scaling capabilities. For this pipeline to scale, the developer doesn't have to write even a single line of code. Julius automatically takes care of scaling, and you can see that the distribution of the nodes is intelligent. It's not distributed randomly. For example, this cluster of nodes are all distributed to the same machine in order to minimize the network traffic, which is critical to performance. The third benefit I want to highlight is the low code aspect. So to define this entire application, 63 nodes and rather complicated logic, a developer only needs to write 33 lines of declarations in our low-code DSL. So just to be clear, this 33 lines of code defines the pipeline with all the connections and dependencies. So in terms of what's happening at the individual node, each node can call any complex function, and that function can be sourced from any library. You can even mix and match libraries in different languages within the same pipeline. Now, the difficult or time-consuming part of pipeline building is the process of stitching these functions together, managing the memory, the hierarchies, distribution, etc. Julius takes care of all of that for you, so you only need to define or declare your pipeline using our low-code syntax. The pipeline is then built automatically without much additional work on the developer side. So I know there's quite a bit of information being thrown your way, but if you want to do a deeper dive into the low-code DSL with some specific applications and examples, we hosted a workshop earlier in the conference, which is accessible on YouTube. So let's move on to the final example, which is based on a much bigger graph that shows the scalability needed to run a bank's risk process. In this case, we're looking at valuing a portfolio of 100,000 trades. So while this graph is rather large with more than 1 million nodes, it certainly doesn't represent the limit. Julius can routinely handle graphs with hundreds of millions of nodes in a distributed manner. In this case, since the graph is so large, it can't be displayed on a single page, but we can still easily navigate the graph. Here we can drill down into the hierarchy of the graph to look at the individual trades and see all of the intermediate steps and how the calculations have been automatically distributed across multiple machines. We also natively support AAD, or adjoint algorithmic differentiation, out of the box, which is useful for financial risk modeling and also backpropagation for ML and deep learning applications. It's a powerful feature that provides for extremely quick sensitivity calculations and for computing gradients. Again, I just want to quickly highlight that to get all these benefits with a very large graph, A developer only needs to write 69 lines of code in our DSL to build this entire pipeline with over 1 million nodes. In practice, the equivalent system at a bank would comprise hundreds of thousands of lines of code or more. So these examples only scratch the surface of what Julius can do. You can appreciate how much faster and easier it is to build data analytics because we automate most of the difficult and tedious tasks. Julius can also be used to refactor existing pipelines in a piecemeal way to be scalable and transparent. So, one of the reasons we started Julius was to offer Julia developers better tools for solving enterprise problems. The powerful combination of Julia and Julia's low code auto scaling graphs produces next generation capabilities and speed. We're helping Julia developers build enterprise solutions in a fraction of the cost and time. Our low code framework is based on Julia syntax, so it's easy for Julia developers to learn and use. And finally, we provide a viable migration path to Julia by allowing organizations to move in a piecemeal fashion without having to recreate their environments or code libraries from scratch. So we appreciate the opportunity to present to JuliaCon. We're excited to work with this community, and we're huge believers in the future of Julia and graph computing. Thank you for listening.
Thanks, James. And thank you, Julius Tech, for being a platinum sponsor at JuliaCon. Please do check out their sponsored forum, which is happening later in the day, and check out the live JuliaCon web app to find out when that is. Next, we want to quickly move on to the annual Julia Developer Survey, which I will start playing in a
Hello, I'm
second.
Andrew Claster with Julia Computing. This is the presentation of the 2022 User and Developer Survey. This is the fourth annual survey we have conducted. This year, we interviewed 1,162 respondents, July 7th to 18th. The survey was administered in 3 languages, English, Japanese, and Spanish. In previous years, and we hope in future years, we intend to include Chinese again as well. You can see the actual question wording of each question just under the black line at the top of the screen. Which of the following languages have you used regularly or frequently during the past year? As we would expect, number 1 is Julia at 85%, followed by Python at 67%, Bash Shell, PowerShell at 42%. Which of the following languages have you used regularly or frequently during the past year? And which do you plan to use regularly or frequently during the next year? 92% of respondents say they plan to use Julia regularly or frequently during the next year, an increase compared with the percentage who say they've used Julia regularly or frequently during the past year. Users and developers plan to use Python less, Bash Shell, PowerShell less, as well as several other languages less. 75% say Julia is one of my favorite languages. An additional 17% say they like Julia, for a total of 92% who say that Julia is one of their favorite languages or they like Julia. Python has continued its decline over the past 4 years. The most popular technical features of Julia are number 1, speed and performance, number 2, ease of use, number 3, open source code is available and can be modified, package manager, multiple dispatch, solves the 2-language problem. The most popular non-technical features are it's free, the community of developers is talented and active, the community of developers is warm and welcoming. The biggest technical problems with Julia are, number 1, packages aren't as mature or as well maintained as I need. Number 2, it takes too long to generate the first plot. Number 3, cannot generate self-contained binaries or libraries such as .exe, .dll, etc. Slow compile times, require packages, libraries, or tools that are only available or are more complete in another language, doesn't have all the packages I need, etc. The biggest non-technical problems with Julia are related to adoption. My colleague's company or collaborators use other languages, there are not enough Julia users in my field or industry, there are not enough Julia users in general, etc. Thinking about the tasks for which you use Julia. If you weren't using Julia for these tasks, what programming language would you be using? Number one is Python at 77%, followed by C++, R, MATLAB, and C. Reasons for choosing Julia. Number one, Julia seems like the language of the future. Elegance of Julia, faster for the work I am doing. Julia solves the two-language problem. I like learning new languages. Where do you interact with the Julia community? GitHub, Discourse, Slack, Stack Overflow, and Twitter are the top responses. Which of the following best describe your use of Julia? Largest share say they use Julia for research, followed by hobby programming, and use Julia for work individually. Which of the following types of Julia packages have you created? Top response is private and not registered in a private registry. Which of the following types of Julia packages have you contributed to, including documentation or filing issues, but not created? Top response is open source and registered in the Julia General Registry. When did you first start using Julia? Most started using Julia in the last 4 years. What percentage of the programming work you do is in Julia? Most respondents do at least 20% of their programming work in Julia. Most popular packages are plots, data frames, benchmark tools, Pluto, differential equations. How robust is the current Julia package ecosystem? 56% say somewhat robust, 73% say either very or somewhat robust. Which editors or IDEs do you use frequently? We've seen a significant increase in the percentage saying VS Code, followed by Jupyter and Pluto. Which cloud solutions, if any, do you use together with Julia? The largest share say none, followed by local cluster, then AWS. How helpful and collaborative is the Julia community? 56% say very, 85% say either very or somewhat helpful and collaborative. Offering JuliaCon online for the past 3 years has dramatically increased the share of respondents who are able to participate in JuliaCon. How did you download or install the Julia version you use most frequently? Nearly 3/4 say binaries from julialang.org, followed by Linux distribution, Julia up, compiled Julia from source. With which operating systems do you use Julia? Top response is Linux x86, followed by Windows, Mac OS, which are growing. Which hardware accelerators, if any, do you use together with Julia? 42% do not use hardware accelerators. That's down from 50% or more in the past 3 years. The largest share of respondents use NVIDIA GPUs. What resources have you found most useful when learning Julia for the first time or when learning how to do something in Julia? Number one, Julia Manual, followed by YouTube tutorials, JuliaCon presentations, Julia books, and Julia Academy. Which of the following do you use as part of your work? Number one, data science, which has increased over the past 3 years, modeling and simulation, statistics, machine learning, visualization, optimization. Which of the following best describes you, academic or professional? Users were also invited to select both. We've seen a significant increase in the percentage who say professional, as well as a decline in the percentage who say academic. Among academics, the largest number of users are graduate or postgraduate students or researchers, followed by faculty, research scientists. Among professionals, the vast majority say engineer or developer. Many also say researcher, analyst, or manager. What is the primary industry in which you work? Among professionals, number one is software, IT, followed by engineering, finance, consulting, life sciences, and healthcare. Among academics, The primary field of study or research for the largest number is computer science, followed by mathematics, physics, and biology. What type of improvements to Julia would make you more likely to recommend Julia to other people? Number one is reduced startup time. How many years of coding experience do you have? Most Julia users and developers have 15 years coding experience or less. The age of most respondents is between 23 and 40. We're seeing growth in the share who are age 36 plus. What is the country or region where you currently live or work? United States is number one, but the Julia community is becoming more diverse beyond the United States as the share based in the US is declining. The biggest increases we've seen since last year are Japan and India. We see a decline in China, but we believe that is largely due to the fact that the survey this year was not offered in Chinese. We hope to rectify that next year and in future years. What is the country or region where you are originally from? Again, US is number one, but the share who are from the US is down compared with last year. India and Japan again show the biggest growth. More than 84 countries and regions are listed below. Again, we believe the decline in China is due to the fact that we did not offer the survey in Chinese this year. Respondents are fluent in 58 languages. Number one is English, at just over 90%, followed by German, French, and Spanish. Japanese and Hindi showed an increase, consistent with the increase in the percentage saying Japan and India in the previous questions. Chinese showed a decline. Most respondents are white or Asian, similar to previous years. 87% identify as men, 3% as women, similar to previous years. 5% identify as LGBTQ, similar to previous years. 31% identify as underrepresented in science or computing. 10% due to age. If you have any questions, please contact me, andrew.claster@juliacomputing.com. Thank you.
Thanks for that presentation, Andrew. With this, we conclude today's live session. Please keep track of everything on the Julia web app, and look forward to the keynote tomorrow by Dr. Hussein Atarwala. I'm certainly looking forward to that. Anyway, thank you all, and I will see you all on Discord.